I welcome you all to the session of engine system and performance, and today we shall discuss about superchargers. We have learned from our internal combustion engine course that superchargers are typically used to compress the intake air, and this particular device or component has manifold applications. But today we shall discuss about this particular element in the context of internal combustion engine. We shall see what are the different methods available to increase or to compress the intake air following this method, that is supercharging. Then if we use supercharger, or if we take an effort to supercharging the intake air, then what are the possible outcomes, what are the different detrimental effects as well. And then finally, we shall discuss about a typical layout of this particular component, that is supercharging. So, to start with, that superchargers are not a recent invention, rather the history of supercharging dates back to eminent scientists in this field, scientists and engineers in this field, Gottlieb Daimler and Rudolf Diesel. So, Gottlieb Daimler first supercharged his engine, as it is apparent from the patent filed by him way back in the year of 1885. What he did to have supercharging, we shall discuss this part, but supercharging of high speed gasoline engines is as old as its type. So, let us write here that, as I said you, it is Gottlieb Daimler and Rudolf Diesel. So, they used supercharging essentially with a specific objective in mind, and that is essentially to increase the density of the intake air, so that the mass of air can be increased. Okay? Because if we can recall, the amount of air that will be drawn into the engine cylinder is essentially the volume or displacement volume. So, if you would like to increase the mass of air, we have to increase the density of intake air. So, for a fixed volume, if we increase the density of intake air, mass will increase, and if we can increase mass of air, larger amount of fuel can be ignited, which in turn will ensure greater power output. So, as I said that Gottlieb Daimler, he first he had supercharged his engine, his first engine, as it is reported in his patent. This patent number is DRP 34926 in the year of 1885. So, you can see that the concept of supercharging high speed gasoline engine has started long back. So, this is not really a new invention. So, and we have also seen that supercharging high speed gasoline engine is as old as it itself. Okay. So, what Daimler did, actually that if you try to recall that the movement of the piston between two centers, and those centers are top dead center and inner dead center. Now, when piston is returning back from TDC to BDC, maybe during intake stroke, during power stroke. So, if we can use the downward movement of the piston rather the end of the piston top is certainly be in touch with always phase charge, combustion product, etc. But at the bottom end of the piston, if we can use that the downward movement of the piston to compress the charge, that means if we can have a cavity in the crankcase and if we allow charging of mass through the cavity of the crankcase, and that charging, that is compression, can be done by the downward movement of the piston. That is what Daimler did long back, and he found that if we can really utilize the downward movement of the piston, that is essentially that we know two-stroke engine. So, the downward movement of the piston, if that movement can be used to compress the charge, which will eventually result higher or greater mass of air can be drawn into the engine cylinder. So, that was his concept. Now, we know very well that supercharging will certainly have a few advantages. On the contrary, it will also have a few disadvantages. So, supercharging first experienced absolute peak in regard to the power output. So, we can tell that having supercharging of the intake air, it was really possible to increase the power output. So, it was experienced peak in the in regard to the power. Also, you know that if it is the engine which is used, say for it was seen, if we go to the next slide, that means we all know that if the engine attains higher altitude, certainly density of the air will reduce. So, then mass of air that will be entrapped during intake stroke inside the cylinder volume will be less because of low density. So, at high altitude the supercharging experienced even better performance, and that was observed during Second World War. So, what I am telling all these things, that supercharging the intake air, it is not new, rather the concept has started long back, and supercharging experienced peak in the power development. It helped to have better performance even when engine or engines attain higher altitude, and it is because of this supercharging that if I write here, so it is because of this supercharging, the supercharging of gasoline, high speed gasoline engine, rather I should say engines, because engines experienced first absolute peak in regard to output power. It helps to obtain better performance when engines are attained high altitude or I should write helped. So, this is, and also that it has been observed that break mean effective pressure BMEP or BMEP, that is break mean effective pressure values were obtained or reached up to 23 bar. Okay. Now, the question is, so supercharging has all these favorable aspects. Now, supercharging can be done by using a mechanical compressor, that means mechanical turbo compressor. So, we need to have one mechanical element or mechanical device that is essentially compressor to compress the air. So, we need to, or we can use even root blowers. So, we need to compress the air, we need to increase the pressure of the air. So, that that can be done by using a mechanical turbo compressor, or there is a provision of using exhaust gases to run a compressor and to run a compressor via small turbine. So, that is known as turbo charging. So, essentially if we use exhaust gases that come out from engine cylinder, and using the exhaust gases, if it is possible to run a small turbine and the turbine can be connected to the compressor, and essentially this particular combination or arrangement is known as exhaust gas operated compressor. So, whether the compressor which will be used to increase the pressure or increase the mass of intake air following enhancement in density of intake air, this compressor can be run either by using a mechanical turbo system or by using exhaust gases. Okay. So, this is the using exhaust gases running a compressor was first came into the market in the US, and that was first introduced by Chevrolet. So, there is a automobile Chevrolet is an automobile company, and that company first introduced exhaust gas or exhaust gas operated supercharging unit, and that was introduced in the year of 1960. So, what we can understand that our objective should be to increase the consumption of air. So, that is, since the displacement volume, that is we know that the displacement of piston from top dead center to inner dead center is remaining the same. So, for a given displacement, if we need to increase the mass of air, certainly we need to increase the density of air, and that can be done by using supercharging, and greater the amount of mass can be entrapped inside the cylinder, larger amount of fuel can be ignited, and we will be getting higher power output, right. So, let us look into and we know that if larger amount of fuel can be ignited or fuel can be burnt, indicated power output will be more. So, indicated power output is directly proportional to the mass of air consumption. Though brake horsepower is not directly related to the mass of air or air consumption, but still that for a given other losses like frictional losses, this brake horsepower is also indirectly dependent on the mass of air to be entrapped inside the cylinder, because higher is the indicated power, higher will be the brake power. So, though mass brake horsepower is not directly dependent on the consumption of mass or air entrapped, air will be air that should be entrapped inside the engine cylinder, but it is indirectly dependent on air consumption. So, we shall now see what are the different methods by which mass of air or air consumption or air to be entrapped inside the engine cylinder during intake stroke can be increased. So, if we write now that possible methods to increase the air consumption of an engine. Possible methods available to increase the air consumption of an engine. So, if we list down the method, first one is essentially increasing the very first idea could be increasing the displacement volume. So, the greater amount of mass can be drawn into or inducted in the cylinder. So, but if we try to increase the piston displacement, if you would like to increase the piston displacement, you can understand that the engine will be bulky, cylinder will be having little larger length, not little rather larger length, and weight also will be more. So, this is again not a viable option probably to increase the air consumption of an engine. Okay. So, this is not possible. So, as I can write here that we will increase weight of the engine, and if we increase the engine cylinder length, cooling or of engine will be a problem. Engine and cooling of the engine will be a problematic issue. Okay. Then number 2 option could be running the engine at higher speed. Okay. So, that this could also be an option to increase air consumption of an engine, but if we allow engine to run at a higher speed, then certainly frictional losses will be more. Over and above, large inertial stress will be imposed on several parts of the engine, because piston is moving at a high speed. So, the stress due to inertia will be more, and that is known as inertia stress. So, that will be rather larger inertia stress will be imposed on several parts of the body. So, this is again not a viable option. So, I can write here larger frictional loss, and this is called greater inertia stress due to higher inertia. So, these two problems or problematic issues are there, and if we write the third option, that is increasing density of air, right, or charge rather. That is what I was talking about in the beginning of today's class. So, if we can increase density, even if we keep the displacement volume fixed, speed fixed, density will ensure higher mass of air to be consumed during intake stroke, and we can really ignite or burn larger amount of fuel. So, that this could be a viable option, because if we use this, then what we can write, that greater mass of air or charge can be inducted into the same volume associated with piston displacement, associated with the piston displacement right, and speed. As such, this option is, this is a viable option. So, this, out of these three different methods that we have discussed, that is increasing the density of air or charge, that is, if we can increase density, then greater amount of charge can be inducted into the same volume associated with the piston displacement and engine speed, and this option can be a viable option among three options that we have discussed so far. So, essentially this is nothing but the use of supercharging. So, that means we need to use mechanical device to increase the density of the that incoming air or intake air, and that can be done by using the or by increasing the pressure. So, if we increase the pressure, so essentially density will increase, and if the density increases, greater mass of or mass air consumption will be higher, and higher amount of fuel can be burned. So, this is what it is. Now, question is that what I would like to tell you, if you would like to increase the density of air, essentially to obtain higher amount of or higher mass of air to be consumed or to be inducted, then is there any specific requirement of the engine design to be, or engine designs need to be changed? No, because only designs of engine will remain same more or less, but what we need to ensure that if we increase, or if we need to increase density via the development of pressure using a compressor, so it would be ensured that engine components or parts will be able to withstand that high pressure. So, this is what it is important to ensure. Okay. So, as I said you, the method, if I write here, that would be nice. So, the device used to increase the density of inlet air is known as supercharger. So, the device used to increase the density of the inlet air is known as supercharger. Okay. So, we will be using this particular method to increase the air consumption rate or mass of air to be drawn into the engine cylinder. Now, this particular device or component can be used even for both 2-stroke and 4-stroke cycle SI and CI engines. So, this supercharging method can be used for both 2-stroke and 4-stroke cycle SI and CI engines, but there are some issues. let me tell you one important point in this context, that we all know that the compression ratio of SI engine is limited to 10 or even 12. So, why it is so? Because for the SI engine, if we increase the compression ratio, then the rise in pressure at the end of the compression stroke will be more, and that pressure may lead to an important undesirable event which is known as detonation. So, essentially to prevent detonation, what is done is the compression ratio is kept low. So, now question is, if we use supercharger for the SI engines, right, whether it is a 2-stroke cycle or 4-stroke cycle engine, then supercharging will increase the pressure of the intake air. Now, that air pressure again will increase during compression stroke. So, as I said that compression ratio is limited or it is low for the SI engines, and hence if we again increase the pressure of the incoming air, then probability of having detonation will be more for the SI engines if we use supercharging. So, that is why SI engine based what is typically superchargers are used for SI engines when SI engines are taken at higher altitude, because at higher altitude air density will reduce automatically with height, and at that height, even if we increase supercharger or supercharging, if we go for supercharging, the rise in pressure will not create any harmful effect to the engine in terms of detonation. So, that means supercharging can be used for, or superchargers can be used for SI engines if the SI engines are taken for higher altitude applications. Okay. So, this is very important. So, just I am writing use of superchargers for SI engines, and this is essentially that so this is limited when SI engines are used for high altitude applications. That means SI engine based aircraft or airplane can use superchargers without inviting problem associated with detonation. Okay. So, this is most important point that I had mentioned. Now, let us discuss about if we really need to go for supercharging, though it will be having some points or some effects in the context of SI engine operation, that superchargers cannot be used always for SI engines. If the SI engine or SI engines are used for high altitude applications like SI engine based airplane or aircraft, then certainly superchargers can be used even without inviting problems associated with the detonation. But then if we need to go for supercharging, what are the different favorable aspects or even detrimental effects are associated with this. So, let us now list down very quickly that effects due to supercharging, right. So, that means if we use supercharger, we will have several favorable even several detrimental effects. So, let us now list down. Number 1 is it increases mixing of air fuel mixture or mixing of air fuel mixture. So, that means it helps to obtain homogeneous mixture of air fuel. For the SI engines, or even as I told you many times, for the modern CI engines, since the fuel is injected through multi-port fuel injection system, sometimes fuels are injected even in the intake manifold, and fuels are fuel which is injected is allowed to mix with the incoming air stream. So, we need to ensure that the fuel which is sprayed into the incoming air stream should be able to mix with the air stream properly, so as to ensure homogeneous mixture. If we need to ensure that, certainly some chaotic environment should be there in the intake manifold. To some extent, the flow environment should be turbulent type. Now, if we use supercharging, the entire purpose is to increase the pressure. If pressure increases, certainly velocity of intake air will increase, though the intake diameter is remaining the same. That higher velocity will create turbulent flow environment, which in turn will ensure chaotic mixing of the air fuel mixture. Rather, it will promote mixing quality of these two different streams, that is air stream with the injected fuel. So, that is the favorable aspect. Okay. So, it will ensure uniform distribution it will ensure uniform distribution of charge in the cylinders and number 2 is homogeneous mixture of air fuel. So, this is very important. Okay. So, this is the favorable aspect. Now, number 2 is the temperature of the charge will increase. Temperature of the charge will increase because compression will lead to increase in pressure accompanied with an increase in temperature. So, this temperature will have some favorable and some detrimental effects. Favorable effects are that if we increase temperature, since fuel is injected in the intake manifold, so the higher temperature will allow fuel droplet to completely vaporize. So, it will help better vaporization of the fuel droplet sprayed into the intake manifold. Now, what would be the detrimental effect? With increasing temperature, the charge or incoming charge temperature will be higher, and if the temperature is becoming higher, that may become vulnerable for the initiation of detonation when that charge will be compressed further, because the charge will be drawn into the intake cylinder and that will be drawn into the engine cylinder during intake stroke. In the intake stroke itself, if the charge is having higher temperature, the temperature will increase even further during compression stroke. So, essentially the chance of having detonation will be more with this particular effect, that is increasing the temperature of the charge. So, despite the favorable aspect of better or efficient vaporization of fuel droplets in the intake manifold, higher temperature may lead to the possibility of having detonation for the SI engines. On the other hand, this higher temperature can reduce the possibility of detonation for the CI engines. So, these two things are there. Okay. Then 3 is, that is most important, if I write here, that is power consumption, power required to drive the superchargers. Okay. So, for this, rise in temperature has several effects. Let me repeat once again. It will promote vaporization of fuel droplets in the intake manifold, but rise in temperature will increase the temperature of the charge even further during compression stroke, and that eventual rise in temperature may become vulnerable for the onset of detonation for the SI engines, but this rise in temperature will reduce the possibility of having detonation for the CI engines that you have studied in your undergraduate internal combustion engine course. Now, let us come to this particular point, that is power required to drive the superchargers. Now, we know that it is a mechanical element, right, mechanical device. So, the compressor will run taking some power input. So, we need to supply certain amount of energy in the form of work, right, to drive the compressor. So, that work will be consumed by the compressor from the output work of the engine itself. So, we are trying to increase the power output by increasing the air consumption rate. Now, out of this output power which will be increased because of the supercharging, if the compressor itself consume a significant part of this power, then eventually it will have no gain. But on the other hand, what will happen, that the entire assembly of supercharging unit will increase the overall weight of the engine, the operation will be noisy. So, what will happen, that we will be having little larger weight of the engine, operation will be noisy, but on the other hand total gain will be 0. So, this part should be taken into account when someone is designing the supercharging unit, so that the power consumption by this unit should not be equal to the power or more power being developed because of this unit. So, with this, if we go to the next part, that is very important, let us discuss about what are the, I was talking about supercharging. So, to increase the density of intake air, we need to have some mechanical components. Typically, these are compressors, or you can use root blowers. So, now let us look into the mechanical devices which are typically used to compress the intake air, essentially to have better performance of the engine. But as I said you, this part should be taken into account, so that the effective power output can be realized with the use of superchargers. So, if we go to the next slide, then we can see typically this is the schematic depiction of root blowers. So, positive displacement type compressors or even root blowers. These are used, you can understand this is two lobe, probably you have studied all these things in the context of turbo machines, because all these are turbo machines and this is 3 lobe. So, what happens, that this is the intake air. So, air is taken to this blower through this path, and when air is passing through this device, the movement of the lobe, I mean this is 2 lobes. So, in the course of its motion inside this device, its pressure increases. Essentially, these are rotating devices, and we are trying to rotate this, taking some power from the engine shaft. So, that power is imparted to the oncoming stream, that is air stream, and receiving that power, air density or air pressure increases. So, this is 2 lobe roots blower, this is 3 lobe. All these are positive displacement type, as if there is a positive displacement of the air volume which is or which was entrapped, and then so basically there will be positive displacement of the air volume which is entrapped here, and then the it would be the air volume will be compressed. So, this is root blower. So, if I write here, so superchargers may include a positive displacement type of compressor or even centrifugal compressor coupled directly to the engine. Okay. So, it is not always a necessity that superchargers should include only positive displacement type. It may also include centrifugal type compressor coupled directly to the engine. So, in the schematic depiction we are showing Roots blower and these are positive displacement type. In a positive displacement type we have studied perhaps in our undergraduate fluid machinery course, there is a positive displacement of the system boundary. So, if we take at a given particular instant of time, the certain amount of working fluid will be taken inside the machine and entire volume will be displaced by the moving boundary of the machine in another stroke. So, in one stroke certain volume or certain amount of working fluid will be drawn into the machine, and as if in the next stroke entire volume will be displaced or entire volume will be discharged by the moving boundary of the machine, and hence there is a positive displacement of the working fluid, hence the name positive displacement is coming. Here if I write in the next slide, so in the schematic we have shown Roots blower and it has two lobes. Roots blowers, it can have 2 lobes, it can have 3 lobes also. So, if I go to the positive displacement type, just I am writing here that positive displacement type. Though you have studied this particular topic in your fluid machinery course, positive displacement of volume of the working fluid, typically air for this case or gas, positive displacement of volume of gas is entrapped in one stroke and compressed and is compressed in another stroke, is entrapped in one stroke and is compressed during another stroke, rather I should write during another stroke by the movement of movement of devices, boundary elements. So, these devices I have written because the device can be blower, this device can be compressor. So, in one stroke the working fluid will be drawn into the machine and during another stroke the entire so in one stroke it will be entrapped, in another stroke the entrapped mass will be compressed and discharged by the movement of the device boundary element. So, this is all about positive displacement type. Okay. So, for the superchargers or for supercharging, Superchargers may include a positive displacement type compressor or even Roots blower, or superchargers may include a centrifugal type compressor as well, and that is shown in this slide. So, this is a centrifugal type compressor. Probably you have studied about centrifugal pump. So, the mechanism of raising pressure is same, only the difference is, we have studied about centrifugal pump wherein the working fluid is an incompressible liquid. So, but here the working fluid is gas or air. Now, in a centrifugal pump, we have studied that blades are mounted on a hub, and hub plus blades, this assembly is known as impeller. While for a compressor, a few blades are mounted on a hub, or this hub plus blades, entire assembly is known as rotor for the compressor. So, in a centrifugal compressor, what is done, you can see from the schematic depiction is that, let me show the arrow here, that will help you to understand. So, this is basically the direction of air entry into the machine. So, this is, air enters in a direction which is known as axial direction. So, this is the axis of the machine. So, parallel to the axis of the machine, air enters into this device, and then that blades are rotating or vents are rotating, and eventually air is discharged in the radial direction. So, you can see this is the radial direction. So, this is basically there is a directional or change in direction of the fluid stream, and that here the device is using centrifugal action to increase the pressure, which in turn will increase the density of the intake air, and hence this is known as centrifugal compression. So, if I write here that centrifugal compressor, as I said you, this type of compressor, is characterized by axial inlet of air and its subsequent radial discharge. Okay. And as I said you that it has, so this hub plus vents or blades, this is known as rotor of the compressor, and it has a group of diffuser vents, while the total pressure rise is equally divided, or the total pressure rise is equally shared or by these elements. So, there are a group of vents which are mounted on this hub, and the entire assembly is known as rotor, and the total pressure developed or total pressure rise is shared equally by all these vents or blades. So, this is all about centrifugal compressor, and superchargers may used, as I said you, or may include both positive displacement type compressor, or it may include centrifugal compressor to increase the density or pressure of the, to increase the pressure of the intake air. So, now let us look into a typical arrangement of the layout of the supercharger. So, that you can see from the schematic depiction, you can see that this is the compressor which is there in the circuit, right. This compressor can be positive displacement type, this compressor can be centrifugal type, but what we can see from this arrangement or block diagram is that compressor shaft is connected to the shaft of the engine. That means the engine and compressor are mechanically coupled. So, these two components are mechanically coupled, and output power of the engine will be used to feed some power to run the compressor. So, that means to run this compressor, engines need to supply certain amount of power, and that is what I was talking about. Designers should be careful so that to run the compressor, the consumption of power should not be equal to the additional power being developed because of this. So, this is what it is. Now, and then this compressed air is fed into the engine cylinder essentially to increase the mass of air or air consumption rate. So, let us now consider this particular unit, and we shall briefly recapitulate our basic understanding of thermodynamics to have some mathematical expression of the total pressure rise or total change in or total the amount of power that you need to supply to compressor for its operation. So, if we take out this particular element and if we write here that we can say that, okay. So, as I said you that advantages of this particular arrangement, advantage is that we can really increase the mass of air to be drawn into the engine cylinder. Disadvantage is it can consume significant part of power output. So, designers will be careful, but best thing is it can adjust to change or change in load condition. So, if any engine needs to experience, or if the engines experience changing load condition, then this particular part is very helpful to adjust to the changed load condition. So, if we take out this particular component and draw here, so we all know the compressor. If we draw, quickly we shall solve this, we shall work out this because you have studied all this. So, this is inlet condition. So, this is inlet to the compressor. So, this is inlet to the compressor, and this is outlet of the compressor. If we consider pressure is Pi, temperature is Ti, these two different, or enthalpy is Hi, and outlet quantities are Po, Ho and To. So, that means this compressor is having this shaft, and this shaft is connected to the shaft of the engine. Okay. So, the incoming air which is taken from the ambience will be compressed to increase its density. So, now you know that if we apply or if we draw the control volume that you have studied in your undergraduate basic thermodynamics course, and if we go to the next slide and if we apply steady flow energy equation. So, if I write, if we apply steady flow energy equation SFEE applied to the control volume around the compressor. Okay. So, this is the CV. Mind it, we are assuming that the compression process is reversible adiabatic process. So, there is no heat interaction. So, around the compressor an adiabatic compression. Okay. So, there is no heat interaction. What we need to do, we need to supply certain amount of work into the system or into the control volume to get this process done, that means to increase the pressure of the working substance. So, if we apply the steady flow energy equation, quickly we can write, if we try to recall, Q dot plus summation of M dot I H I plus V I square by 2 plus G Z I equal to W dot plus summation of m dot E He plus V square by 2 plus GJD. So, this is the steady flow energy equation. We have only one inlet and one exit. So, we can assume that m dot I equal to summation of m dot E equal to m dot. Okay. So, we can write these two equations. These two equations are applicable to describe the process that takes place across this compressor. And if we ignore, but we can change, we can consider that change in kinetic energy and potential energy is negligible as compared to change in enthalpy. So, height of the compressor is very low. So, change in elevation, that is change in potential energy, can be ignored as compared to change in enthalpy. We are also going to consider change in kinetic energy is small as compared to change in enthalpy. If it is so, then from there, and there is no heat interaction between the compressor and surroundings. So, that means we can write Q dot equal to 0. If this is the case, then we can use this equation to write that Hi, that we can write Hi into m dot, we can write here that equal to W dot plus m dot into He. So, we can write W dot equal to m dot into Hi minus He, right. So, that is the work which is needed to run the compressor. Mind it, typically in thermodynamics we consider work added to the system is negative and heat added to the system is positive. So, what we consider, convention is heat added to the system is positive and work is done by the system is positive. So, this work which we need to supply to the control volume is, it should be m dot into He minus Hi. So, because this is negative work. So, this is the W dot for the compression process. So, this is the work to be added so this is work to be added to the compressor. Addition of energy in the form of work, okay. And now we can write, if we assume that air to be heat specific is remaining constant, then we can write W dot, and that is the this is not the actual work. So, this is the ideal work, that equal to m dot into Cp into T naught minus Ti, because while we have estimated this work which is needed to be added to the compressor for its operation, we did not take into account the frictional losses. So, this is the ideal work done. If we go to the next slide, then we can figure out mechanical efficiency of the compressor. Okay. So, mechanical efficiency of the compressor equal to, so m dot into T naught minus Ti into Cp divided by W dot actual, because actual work which we need to supply to the compressor should be much higher than this amount, because frictional loss, we need to supply certain amount of work to overcome the frictional losses. So, from there we can calculate W dot actual equal to m dot Cp into T naught minus Ti divided by eta mechanical, right. Now, question is, to close this equation we can have, so essentially we need to know the rise in temperature rather what is T naught minus Ti. So, for that let us consider the expansion of the or compression of the air. So, if we consider these two pressure P1, 2 or so this is Pi, this is P naught. So, this is T, this is S. So, this is basically 1 to OS, whereas the actual compression process will be like this. So, this is O. So, now, so this is the actual compression process, while this is the isentropic compression process, right. So, from there we can define isentropic efficiency of the compressor, that is nothing but rise in temperature following isentropic process divided by rise in temperature following actual process, right. So, that means if we would like to close this equation, we need to know about this quantity T naught minus Ti, then we can write from here that T naught minus Ti equal to T OS minus Ti divided by eta S, and we can write one step further, that is To minus Ti, that is T out minus Ti equal to Ti divided by eta S into TOS by Ti minus 1. So, for this reversible adiabatic process, so isentropic process, so for the isentropic process we can write T naught S by Ti or TOS by Ti equal to P2 by P1 or P2 or PO by, sorry, this is PO. So, this is PO by Pi power, this is PO by Pi power gamma minus 1 upon gamma. So, if we plug in this expression, then we can write T naught minus Ti, that equal to Ti divided by eta S into P naught by Pi power gamma minus 1 upon gamma minus 1. So, that is the change in temperature. So, this PO by Pi is known as compression ratio, sorry, pressure ratio. So, this is known as pressure ratio. So, this is known as pressure ratio. So, rise in pressure because of this compression process. So, try to understand, had we following this compression process, we could somehow, if we go back to the previous slide wherein we have written W dot actual that we need to supply to the compressor should be equal to this quantity if we know the mechanical efficiency, and T naught minus Ti that we have established in terms of pressure ratio. So, this mathematical expressions will be needed for solving a few numerical problems that we will do in our next class. So, if you would like to summarize our today's discussion, we have discussed about superchargers, the need of supercharging in the context of internal combustion engines, what are the different avenues by which we really can go for increasing the density of intake air, and we have discussed about merits and demerits associated with each and every methods. Thereafter, we have discussed about what are the outcomes of a particular method, that is supercharging, that is if we need to go for compressing or compression of the intake air. Then we have discussed about different types of compressors used for supercharging, and finally we have mathematically established some expressions, those are very useful to solve numerical problems. With this I stop here today, and we shall continue our discussion in the next class. Thank you.